All right, guys, so this is part 2 of limits to infinity. So there are some quick rules that will help you figure out limits of infinity for rational functions, right? So when there's a numerator and denominator. So it says here, if finding the limits as x approaches infinity for functions with x in the numerator and denominator, so something like this, you'll end up with infinity over infinity. So an alternative method must be used. One method is that you can simplify the expression by factoring things out, right? Like we've practiced before, doing it algebraically. But sometimes it doesn't work, like here, right? If we plug in infinity, we're going to end up with 3 times infinity plus 5 over 7 times infinity minus 2. You end up with infinity over infinity. And then I look at it, I can't factor anything out. So there's an alternative method. And that alternative method is to divide each term in both the numerator and denominator by the highest power of x. So for example, for this first one, the highest power of x that I see is just x, right? X to the first. So let's divide each term by that highest power. So 3x over x plus 5 over x all over 7x over x minus 2 over x, right? And this is that part where algebraically you could start plugging in that number. But here we're dealing with infinity. So how do we plug in infinity? Well, first I can simplify. Like I know those are going to cancel out, right? So I end up with the limit as x approaches infinity of 3 plus 5 over x over 7 minus 2 over x. Right? So now, if I plug in infinity, let me get a different color here. If I plugged in infinity here, and I plugged in infinity there, let's think about what would happen to the graph. 5 divided by infinity, well, that's going to be a tiny, tiny number, right? It essentially is going to go to 0, 5 divided by infinity. So I'm going to write that's approaching 0. Same thing here, 2 divided by infinity. It's going to get, it's very small, right? You can imagine that's getting 0. 2 divided by a very, very large number. So then when I rewrite this, this is equal to the limit as x approaches infinity of 3 plus 0 over 7 minus 0. And hopefully now you can see that that is going to be equal to 3 over 7, right? So this one I couldn't factor anything out, so I went ahead and divided everything by the highest power of x, which was x. Found out that these two terms approach 0 because they're infinitely small when you're dividing by infinity, which left us with just 3 plus 0 over 7 minus 0, which is that property of a constant term. So therefore this limit is equal to 3 over 7. And if we graphed it, we could see that. But I'm not going to graph this one. I'm going to graph the next one because I have it ready. All right. So now let's try this one. So can't factor anything out. I'm just going to tell you that. And I'm going to divide by the highest power of x. So the highest power of x here is x squared. So this whole thing is going to be equal to the limit as x approaches infinity of 8x squared over x squared minus 4x over x squared. Whoops. Plus 1 over x squared. Now I do the same to the denominator. 16x squared over x squared plus 7x over x squared minus 2 over x squared. All right, now if I simplify some things out, that's going to give me the limit as x approaches infinity of 8, right, because those cancel out. This x up here cancels out with the square term, so it's minus 4 over x. This is still plus 1 over x squared. Nothing to simplify there. All over. That cancels out. 16. This cancels out with the squared, so it's plus 7 over x. And then minus 2 over x squared. Now let's think about it how we did this. So 8 is 8, right? Okay, 4 over infinity. 4 over infinity is going to be a really small number. We're just going to say it's equivalent to 0. Same thing, 1 over infinity squared, it's infinitely small. 2 over x squared, infinitely small. 7 over x, infinitely small. So what am I left with? I'm left with the limit as x approaches infinity of 8 over 16. Well, that's just going to be equal to 1/2, right? And so let's just check that. I have it here on my calculator. Let's graph it. and hopefully you guys can see that here is that line as we're going towards positive infinity. It's approaching 1/2, but it never gets to 1/2. And you can do this on Desmos C and you can, as well, and you can see it even better. So this makes sense. As the function approaches infinity, as x approaches infinity, the function approaches 1/2. So that is how we do that. So now let's look at these patterns. What happened here? The answer to this was 3/7. The answer to this limit was 1/2, or 8/16. So really we can take these examples and generalize them to rules. So what I'm going to start with first is actually the last rule, because that's what we just did, right? So we said if the highest power of x, what we just figured out, is the same in both the numerator and denominator, then the limit as x approaches infinity is the coefficient of the highest term in the numerator divided by the coefficient of the highest term in the denominator. There's pigeons outside my window having a war. Hopefully you guys can't hear that. So if you look back at this example, that's exactly what happened. The highest power was x, and it was true for both the numerator and denominator. So the answer to that limit was 3/7. Here the highest power was x squared in both the numerator and denominator. So the answer was 8/16, which we simplified to 1/2. So that rule we just proved in our first two examples. Let me move that up. Pause it if you need to write it down. Okay, so what happens if that's not the case? So let's look at the first one I have here. What happens if the highest power of x is in the numerator? So here, for example, the highest power of x is x cubed, and that's in the numerator. There's an x squared in the denominator, but that part doesn't matter. It's just that the highest power is in the numerator. The rule tells us that this function does not exist. So let's prove that. Okay, so let's do what we did for the last one. So this thing is going to be equal to the limit as x approaches infinity of x cubed over x cubed minus x squared over x cubed over x squared over x cubed plus 5/x cubed. All right, so let's do what we did before. If I plug in infinity here, I end up with, well, first of all, this whole thing can cancel out, right? So it's 1, right? So we have 1 minus, well, what happens here if we plug in infinity squared over infinity cubed? Well, infinity squared over infinity cubed, is that going to get close to infinity or 0? It's actually going to get closer to 0, right? So let's think about it. Let's go with this one. So if we have this one, hopefully you guys can see from before, is 0, right? 5 divided by infinity is going to be really close to 0. So now let's go up to the top part. If I plug in infinity over infinity, well, what happens? Infinity over infinity, it's just going to be an infinite number. Same here. This is going to be an infinite number, infinity divided by infinity. It's going to be a really large number. So when we're dealing with this thing, 1 minus infinity over infinity plus 0, we're really ending up with infinity over infinity, which means the limit does not exist. And if we graph that, let's see what happens. So let's graph this. So x cubed minus x squared, all divided by x squared plus 5. And so we can see what's happening as this limit goes to infinity. It's approaching infinity, right? So that's why it does not exist. So it's getting larger and larger. So really, you don't need to evaluate this every time. You just start to go in your head, oh, the highest power of x is in the numerator, the limit does not exist. And you'll be able to just do that because these will become small parts of bigger problems. And if you need to explain it, you can say, since the highest power of x is in the numerator, the limit of this function does not exist. That's a valid explanation. All right, what about the last case, when the highest power of x is in the numerator? It says that then the limit as x approaches infinity is 0. So let's check that out. So the highest power is x to the 4th. So I'm going to do 3x cubed over x to the 4th plus 6x squared over x to the 4th, 7x to the 4th over x to the 4th plus 2x over x to the fourth. Now when I simplify that, I get, this becomes 3 over x, right? Because those x's simplify, cancel out, plus 6 over x squared, right? Over 7 plus, this ends up 2 over x cubed. Right, so now let's look at that. 3 over infinity, we already know that's going to get close to 0. 6 over infinity squared is going to get close to 0. 7 is 7, fine. And then 2 over x cubed is going to get close to 0. So what we're left with is 0 plus 0 over 7 plus 0. So now we have this whole thing is equal to the limit as x approaches infinity of 0 over 7. So the value of that is just 0, right? So you can have a 0 in the numerator of a fraction. And if you graph that, you'll be able to see that it approaches that. So I can type it in real quick so we can see. Let's type it in for clear that out. So let's type it in. 3x cubed plus 6x squared. Close it. Divided by 7x to the fourth plus 2x. All right, and so you can see as this function approaches infinity, that the function's getting closer to 0. It is approaching 0, which is how we got this answer. So really these 3 rules right here, you can always, if you forget, do this process of plugging in the highest or dividing by the highest power of x, but you can also just commit these to memory because when you see them, it's a thing you can do quickly, which you'll see in some of the multiple choice practice today. All right, till next time.